Welcome to Chapter 5 of BADM323, IT Infrastructure and Emerging Technologies. When the phrase information technology infrastructure is mentioned, most people immediately think of just hardware and software. However, there is more to it than just those two. In fact, the most important and often most ignored component is that of services. Integrating all three components forces a business to think in terms of value and the whole and not just the parts. Including all three components in any discussion of IT infrastructure truly fits the cliché that the whole is greater than the sum of the parts. Defining IT infrastructure. If a firm's IT infrastructure is defined in terms of technology, the discussion is limited to the hardware and software components. By broadening the definition to that of service-based, the services generated by the first two components are brought into the discussion. Also, including the PERSware element that we discussed in Chapter 1. Do you remember PERSware? It's the people aspect of an information system. It's kind of an impersonal way of referring to people as a resource. As technology advances the types of hardware and software available, it becomes more critical for the firm to focus on the services that a firm can provide to its customers, suppliers, employees, and business partners. To round out the list of IT infrastructure components, you need to add the following services to computing hardware and software. Computing services provides the platforms that ensure a coherent digital environment. Telecommunication services determine appropriate data, voice, and video that connect employees, customers, and suppliers. Data management services not just store, but manage massive amounts of corporate data and make it available for users to analyze. Application software services, enterprise resource planning, customer relationship management, supply chain management, and knowledge management systems. When we talk about physical facilities management services, we're referring to the physical installation of computing, telecommunications, and data management services. IT management services, they plan and develop infrastructures, coordinate IT services among business units, account for IT expenditure, and provide project management services. When we look at IT standard services, this develops the policies that ensure interoperability of all IT infrastructure components. IT education services, they train employees to properly use IT investments and educate managers about planning for and managing the investments. IT research and development services, they research future IT projects and investments. The service platform perspective refers to analyzing the actual services enabled by new technology tools. For example, a new PC might save an employee 1 hour per day in wait time for information, dramatically increasing his or her value to the firm. The point of this slide is to illustrate the centrality of IT infrastructure and services to the achievement of a firm's success. Ultimately, the firm delivers to customers its quality is a direct function of the power of its infrastructure. For instance, Amazon is routinely cited as the most popular online shopping site and receives high praise for customers for the quality of its service and speed of execution. There is a reason for this. Amazon has one of the largest computing infrastructures, numbering several 100,000 processors to provide these services. If we look at this connection between the firm, IT infrastructure, and business capabilities, notice all the different components on this diagram. We have key systems, mobile users and field sales, switched LANs, which is local area networks. We have websites, remote access services, switched LANs, telecommuters and remote users, switched LANs again, and so on. There's a lot of components that make up an IT infrastructure. So this discussion, we're going to go ahead and talk in detail about many of these. I do want to let you know that this is a very technical discussion. However, I think if we keep it in context of the business, we should be able to get through it with a good understanding of what it takes to implement an IT infrastructure within an organization and kind of have a high level understanding of all the components. There are probably as many definitions of IT infrastructure as there are IT organizations. However, IT infrastructure consists of the equipment, systems, software, and services used in common across an organization. Regardless of the mission, program, or project, it serves as the foundation upon which mission, program, and project specific systems and capabilities are built. This is according to CIO.gov. IT infrastructure refers to the composite hardware, software, network resources, and services required for the existence, operation, and management of an enterprise IT environment. It allows an organization to deliver IT solutions and services to its employees, partners, and/or customers, and is usually internal to the organization and deployed within owned facilities. Typically, a standard IT infrastructure consists of the following components: hardware, which are the servers, computers, data centers, switches, hubs, and routers. Software encompasses enterprise resource planning, we mentioned this last week, and customer relationship management, productivity applications, and more. The network enablement, internet connectivity, firewalls, and security. And we talk about meatware, which is human users such as network administrators, developers, designers, and generic end users with access to any IT appliance or services are also part of an IT infrastructure, specifically with the advent of user-centric IT service development. You may be unfamiliar with the concept of a mainframe computer. We're going to kind of go through the progression of computers from start to where we are today to kind of give you a background of the progression of computers in technology. We're then going to go ahead and look at the progression of the IT infrastructure and how that infrastructure ties all this hardware together. The evolution of a computer is an interesting process. Instead of developing from small-sized machines into huge ones, the computer actually shrinks during the evolution. In fact, the first computer, named ENIAC, which stands for the Electronic Numerical Integrator and Computer, was announced in 1946, and it was a behemoth of a computer. It contained 17,468 vacuum tubes, 7,200 crystal diodes, 1,500 relays, 70,000 resistors, 10,000 capacitors, and around 5 million hand-soldered joints. It weighed 30 short tons, which is about 27 tons, and was roughly 8.5 by 3 by 80 feet. And took 680 square feet and consumed 150 kilowatts of power. ENIAC was designed to calculate artillery firing tables for the United States Army's Ballistic Research Laboratory, but it first was used in calculations for the hydrogen bomb. When ENIAC was announced in 1946, it was heralded in the press as a giant brain. It boasted speeds of 1,000 times faster than electromechanical machines. It was a leap in computing power that no single machine has since matched. Now let's go to the main focus. The size and the power featured by ENIAC are all the typical traits of a mainframe computer system. In fact, ENIAC was the first mainframe computer ever created. Some interesting facts to note about mainframe computers. They're typically huge in size, can take up to a whole room of space. They were very expensive and could cost up to millions of dollars for a single system. They're very expensive to run, considering the size and performance of the computing system. They have the ability to host multiple operating systems. Very powerful, has a high processing speed and huge storage capacity. They are highly secure and reliable due to the graceful degradation property, to continue operating properly in the event of the failure of one or more faults within some of its components, and the allowance of services during operation. They have the ability to support multiple users. It's crucial for organizational operation. It can add or hot swap systems capacity non-disruptively and granularly. What we mean by hot swapping, it simply means that a component can actually be swapped out without turning the machine off. It's kind of like a hard drive. If you take your hard drive out of your computer, your system won't work properly. But in systems where we have redundancy in hard drives, we can actually remove a hard drive and replace it without even turning down a server. So that's what hot swapping means. Mainframes Can have peripheral processors which manage the IOs, which is the inputs and outputs devices, leaving the CPU to deal only with high-speed memory. And oftenly, mainframes are nicknamed Big Iron. The IBM Dictionary of Computing defines mainframe as a large computer, in particular one in which other computers can be connected so that they can share facilities that the mainframe provides. For example, a System 370 computing system to which personal computers are attached so that they can upload and download programs and data. The term usually refers to hardware only, namely main storage, execution circuitry, and peripheral units. Maintenance and operation of these early computers systems were extremely complex and massive cables were required to connect all the components. Old computers also required an enormous amount of power and had to constantly be cooled to avoid overheating. The complexity of these huge room-sized machines required a lot of space and controlled environment, and maintaining these machines also led to the practice of secluding them in a dedicated room. It was the birth of a data center. From the 60s, computers stopped using vacuum tubes to gradually using transistors, which made them more durable, small, efficient, reliable, and inexpensive. The first transistorized computer, known as TRADIC, T-R-A-D-I-C, was developed in 1954, but the commercial models have emerged only a few years later with the first IBM systems. While mainframes were occupying large rooms and consuming huge resources in the mid-60s, a new type of machine appeared. They were smaller and cheaper in the mammoth of mainframes. They were called mini-computers, exactly by opposition to the gigantic dimensions and price of the predecessors. This type of computer eventually asserted itself, creating a class apart with its own architecture and operating system. In 1971, Intel launched the first commercial microprocessor, a 4004, which was a huge technological leap. This increased in performance of all the systems created the need to optimize the use of an expensive mainframe hardware, separating it into smaller units in order to take full advantage of the still scarce computing resources. This is how virtualization came to be. Very basic in the beginning, but conceptually evolving more rapidly in order to allow the mainframe applications to perform several tasks concurrently. The first commercial use of virtualization was released in 1972 on the IBM VM370 operating system. Moreover, the emergence of the microprocessor soon made the term minicomputer mean a machine that lies in the middle range of the computing spectrum, in between the smallest mainframe computers and the brand new microcomputers. These mid-range machines grew to have relatively high processing capabilities and were used in industrial process control, telephone switching, laboratory equipment control, and in the 1970s they were the hardware platform that launched the computer-aided design, or also known as the CAD industry. So the general purpose mainframe and microcomputer era, which was 1959 to present, the introduction and continued use of mainframes. Mainframes were the first powerful computers that could provide time sharing, multitasking, and virtual memory, and became powerful enough to support thousands of remote terminals. The mainframe era was a period of highly centralized computing, controlled by programmers and system operators. Minicomputers, powerful yet less expensive computers, began to change this pattern, allowing decentralized computing customizable to individual departments or business units. The mainframe has come a long way. The modern-day mainframe, such as the IBM Z series, has up to 101 central processors, also known as central processing or CPUs, has up to 78,000 million instructions per second, and 5.5 gigahertz of quad-core chips. Remember what I mentioned, the first mainframe could process several thousand computations per minute or per second? 78,000 million instructions per second, also known as MIPS. It's a long ways we've come in just a very short time. So I also mentioned 101 central processors. I want to explain what a central processor is. It's the part of the computer, also known as a microprocessor chip, that does most of the data processing. The CPU and the memory form the central part of the computer to which the peripherals are attached. This MIPS, which is million instructions per second, is the general measure of computing performance and, by implication, the amount of work a larger computer can actually do. For large servers or mainframes, MIPS or MIPS is a way to measure the cost of computing. The more MIPS delivered for the money, the better the value. Historically, the cost of computing measured in the number of MIPS has been reduced by half on the annual basis for a number of years. The mainframes are indeed impressive in terms of power and size. However, there's some drawbacks that prevented them from being used by daily computer users like most of us. The truth is, mainframes are just too bulky to house and too expensive to operate for the average folks. So, to deliver the computer technology to the mass, computer manufacturers had to come up with something that can fit easily into our daily life. As a result of this demand, eventually microcomputers were born. However, there's also a catch. The transformation from mainframe to microcomputer didn't just happen overnight. There's one important transition stage where one type of computer was introduced, the minicomputer. The first successful minicomputer was Digital Equipment Corporation's 12-bit PDP-8, which cost about $16,000. Today, that would be equivalent to about $93,600. Upwards, and was actually launched in 1964. The existence of the important precursors of the PDP-8 included a PDP-5. The PDP-1 suggests that minicomputers were invented a few years back earlier though. So the minicomputer is also known as a mid-range computer. They had relatively high processing power and capacity that mostly would fit the needs of the mid-range organizations. They were used in manufacturing processes or handling email that was sent and received by a company. They usually took up one or a few cabinets the size of a large refrigerator or two, compared with mainframes that would usually fill an entire room. Some facts about the minicomputer. It utilizes transistors and core memory technology. It sits in the spectrum between a mainframe and a microcomputer in terms of size and processing speed. It runs full multi-tier users, multitasking operating systems such as VMS or Unix. It's commonly used as servers in a network environment, and hundreds of personal computers can be connected to the network with a minicomputer acting as server-like mainframes. Single-user minicomputers are used for complex designing tasks. The first commercially successful minicomputer was the PDP-8. They were typically successful between the 1960s and 1970s. However, their reign ended when microcomputers emerged during the 80s and 90s. The change in the trend was made possible with the lower cost of microprocessor-based hardware, the emergence of inexpensive and easily deployable local area network systems, the emergence of microprocessors, and the desire of end users to be less reliant on inflexible minicomputers, manufacturers, and IT departments or data centers. This resulted in the minicomputers and dumb terminals being replaced by networked workstations and servers and PCs in the latter half of the 1980s. During the 1990s, the change from microcomputers to inexpensive PC networks was cemented by the development of several versions of the Unix to run on an Intel 86 microprocessor architecture. This included systems such as Solaris, FreeBSD, NetBSD, and OpenBSD. Also, Microsoft Windows series of operating systems, beginning with Windows NT, now included server versions that supported preemptive multitasking and other features required for servers. As microprocessors have become more powerful, CPUs built up from multiple components, once the distinguishing feature differentiating mainframes and mini-systems from microcomputers, have become increasingly obsolete, even in the largest mainframe computers. So this microcomputer is a computer with a microprocessor and a central processing unit. They are physically smaller when compared to a mainframe and minicomputers. Many microcomputers, when equipped with a keyboard and screen for input and output, are also personal computers in a generic sense. Some facts about microcomputers. They're physically considerably smaller than mainframe and mini computers, have a microprocessor and a central processing unit. The most common type of computer in existence today is a microcomputer. PC and PC-compatible computers have processors with different architectures and processors than Apple computers. These two types of computers also use different operating systems. PC and PC-compatible computers use the Windows operating system, while Apple computers use a Macintosh operating system, also known as Mac OS. The majority of microcomputers sold today are part of the IBM compatible. However, the Apple computer is neither an IBM nor a compatible. It is another family of computers made by Apple Computer. They also come equipped with at least one type of data storage, usually RAM, also known as RAM, but most are equipped with secondary non-volatile data storage. They are normally served as a single user and can be modified to serve multiple users. The first microcomputer was designed in 1975 and was based on the Intel 8080 CPU, and it was the Altair 8800 as shown on the screen here. There's a kit that was allowed users to build in Altair, and it costs about $621. That would be approximately equivalent to about $2,127 today. For those of you with knowledge about memory, the Altair 8800 came with only 32K of memory. Notice this is not 32 megabyte of memory, this is 32K. It also came with an 80 by 40 VGA video compatibility. Compare that with the 1920 by 1080 standard resolution today. Reviewing the evolution of corporate IT infrastructure offers some insight into where we may be headed. The general purpose mainframe and minicomputer era, which was 1959 to present as previously mentioned, it's the mainframe era that began with highly centralized computing with netbooks of terminals concentrated in the computing department. While early models contained proprietary software and data, today's mainframes are able to process a wide variety of software and data. It's interesting to note that IBM began this era and remains the sole supplier of mainframe computing. Although the experts and pundits predicted the death of the mainframes in the 1980s, they have evolved and remain a strong, viable component in many IT infrastructures because of their ability to store and process huge amounts of data and transmissions. Minicomputers helped usher in the concept of decentralized computing. So when we look at the personal computer era, which was 1981 to the present time, it's interesting to note that the advances developed for personal computers in the home have given rise to much of the advances in corporate computing in the last 25 years. As the home user became more comfortable with using computers and more applications were developed for personal computers, employees demanded increased use of computers in the workplace. While the Wintel PC standard has dominated this era, open source software is starting to put a big dent into the stronghold. So we look at client-server era. This is 1983 to the present. As the desktop and laptop personal computers became more powerful and cheaper, businesses began using them to replace mini-computers and some mainframe computers by networking them together. Think of an octopus, with the body representing the server and the tentacles representing the clients. At the heart of every network is a server. It can be a mainframe, mid-range, mini-computer, workstation, or a souped-up personal computer. It's where some of the data, application software, and other instructions are stored that network users need in order to communicate with and process transactions on the network. Large companies use a multi-tiered client-server architecture that has several different levels of servers. One of these is a web server. As the name implies, it provides web pages to users. The client computer is the model on the network that users need to access and process transactions and data through the network. Rather than one server trying to do it all, each server is assigned a specific task on an application server. Dividing tasks among Multiple servers allows faster, more efficient responses that cost the business less to produce than a mainframe would, or one computer trying to do it all. When we look at the enterprise computing era from 1992 to present, perhaps no other era has seen the explosive growth in functionality and popularity as this era. The problems created by proprietary, closed systems are being solved by the standards and open source software created in this era. The promise of truly integrated hardware, software, and services is coming true with the technological advances in the last 15 years. On the other hand, the promises of delivering critical business information painlessly and seamlessly across all organizational levels are made all the more difficult to meet because of the ever-changing landscape of technology products and services. When we look at cloud and mobile computing era, this ranges from 2000 to present. It almost seems as though we've come full circle with the concept of cloud computing. This model of computing relies on a massive computing centers owned by the likes of Google, IBM, Microsoft, and even Amazon.com. What is Google's cloud? It's a network made of hundreds of thousands, or by some estimates 1 million cheap servers, each not much more powerful than the PCs we have in our homes. It stores staggering amounts of data, including numerous copies of the World Wide Web. This makes searching faster, helping ferret out answers to billions of queries in a fraction of a second. Unlike many traditional supercomputers, Google's systems never ages. When its individual pieces die, usually after about 3 years, engineers pluck them out and replace them with a new, faster box. This means the cloud regenerates as it grows, almost like a living thing. This is according to the Google and Wisdom of Clouds by Businessweek, December 24, 2007. As you realize that each era built upon previous advances made in hardware, software, and services, let your imagination drift for a moment to the possibilities that the future holds. It truly is an exciting time to be involved in technology. Examples of the use of cloud computing are Google Apps, Google suites of software applications, and rivals of Microsoft's Office applications at a fraction of the cost, and Salesforce.com's CRM management system, which we'll cover later in this chapter. It delivered over the internet. Most large Fortune 500 firms have some applications that run in the cloud. Most of these same corporations do not put their strategic or critical systems on the cloud just yet because of lingering concerns about reliability and security. To recap the evolution of computers, the 1940s, the ENIAC, the first mainframe computer, was invented. In the 1960s through 1970s, the mini-computers replaced the mainframes in most applications, being smaller and cheaper to operate, but still powerful enough to do the job. In the 1980s and 1990s, the mini-computers gave way to the microcomputers due to the lowered cost of hardware and emergence of new network technologies. So if we look at the diagram I have displayed here, the mainframe started out, it evolved to the mini computer, it went to the portable computer, then to a PDA, or to a cellular phone, and then eventually into these microcomputers and PCs. But notice on the very bottom, the mainframe has remained. This slide shows a portion of figure 5.2 that illustrates the first 3 eras of IT infrastructure and evolution discussed in the previous slide. It explains that the yellow ring connecting the machines in the client-server graphic represents a local area network. Personal computers were standalone systems prior to the development of the local area networks. This slide shows the portion of figure 5.2 that illustrates the last 2 eras of the IT infrastructure and evolution discussed in the previous slide. The enterprise internet graphic represents several individual networks linked together to an enterprise-wide network. The cloud computing graph represents several types of technology that are capable of connecting to the internet and accessing applications and services through a cloud. This is a learning track on the stages of the IT infrastructure evolution. The distribution of computing power across smaller, less expensive machines enabled by client-server computing is in part responsible for the drastic decrease in computing power and applications throughout the firm. Prior to small, less expensive server computers, computing power had to be purchased in large blocks at great expense. With client-server computing, you can grow your firm's inventory of computers gradually, over time, to meet current demand.
At ESPN.com, we service literally tens of thousands of requests per second. Let me say that number again, 10,000 plus requests a second. In 1 second, over 10,000 requests come in, and it's not like 1 second goes by and then a minute later we get another 10,000 plus requests. It's relentless. Every second for hours during events, we get 10,000 plus requests a second. The way we scale to that number, or the way we did scale to that number, is a heavy reliance on web page caching. That's critical for us. That doesn't work so great for personalized content. All right, how much data are we talking about? A gig, 2 gigs? No, that's the next part of the problem. We need to store over 10 million users. We have more than 10 million users, but as far as personalized folks, we need to plan for 10 million plus. On average, each of these users takes about 5 kilobytes of data. Some a little bit more, 100K, 200K, some less, but on average, we're looking at about 5K. With full redundancy, if you do the math out, we need to handle or store 200 gigabytes of data. That's certainly not going to fit into 1 JVM, or 2, or even 100. Let's make things more complicated for good measure. On top of all this, we need to leverage this same personalization system for our mobile websites, for soccernet.com, and for deportes.com. The whole point of personalization is not just about personalization, it's also similar to single sign-on. When you tell us what your favorite team is, when you go to ESPN.com, we want that same preference to carry forward on our iPhone Score Center device, on your BlackBerry device, on any device you have, and other websites we own, such as soccernet.com and deportes.com. So how did we do it? This is the fun part. I couldn't wait for this part. So I'm going to describe how we built this quickly, and this is a lot of fun here. So it all starts with a relational database like any other enterprise-grade system. Ours is called the Personalization DB. We weren't very creative with the name. Then we introduced 2 new exotic components, the grid, which you've been waiting for, and the composer. The grid is using IBM WebSphere Extreme Scale. It's effectively an in-memory representation of everything in that personalization DB. The key to this is it's extremely fast. We're talking sub-millisecond response time. The composer is the next part of the equation. The composer facades the complexity in dealing with our existing services. But let me take a quick step back. When a lot of people think of ESPN.com, you might think of 1, 2, maybe 3 services for ESPN.com. That's not the case at all. We literally have hundreds of back-end systems powering our website. The composer brings them all together. It facades the complexity of dealing with all our services, and it knows how to speak with a grid. So let's see it in action. A user request comes in, or in our case, thousands and thousands come in at the same time. They queue up on the composer, and the composer knows how to talk to the grid. It goes to the grid and gets your preferences. Again, lightning fast, sub-millisecond response time. The composer now knows, based on your preferences, which of our services to go to. So for example, if you're an MLB fan, we'll go to the MLB service. If you're an NFL fan, we'll go to that. And we'll go to multiple services if we need to. From that, the composer is intelligent enough to build a response back for you, the fan, and you get your personalized content. Now the key point here is from the moment a user request comes in to the moment it goes out, we're in single-digit millisecond response time. It's extremely fast, and that's why it scales the way it scales. So how does it scale? Fast. The grid is based on 10 physical servers. These are commodity servers. These aren't mainframe multi-million-dollar boxes. These are pretty commodity servers. There's 10 of them. Each have 32 gigs of RAM. We chose to use 20 of those 32 gigs of RAM for a grand total of our 200 gigs. We're using Extreme Scale to power the grid. We loaded 12 million users into this system, and we had 40% room to grow. We're utilizing a few really cool features of Extreme Scale that actually compress the size of these objects so we get more bang for the buck. We threw 12,000 requests a second, and then we threw 15,000 requests a second at the grid. And here's the best part. Not only did it handle it, CPU on all 10 of the servers stayed below 5% the entire time. We never go above 5%. And this is an interesting feature here. So we obviously overbuilt a little bit. Another really cool feature of the grid is you can dynamically, at runtime, so our service is running, we can spin down servers and we can spin up servers if we need to. So if we underestimate it, if we need another 10 servers, we can jump to 20 servers right away. If, on the other hand, as in our case, we have 10 servers and we only need, say, 5 or 6, we can drop the other 5 or 6 at runtime. And on top of that, we have full redundancy. Any one of our servers can go offline at any time, and we don't skip a beat. The grid automatically repartitions everything and puts data where it needs to go. So how long did it take to do this? 1, 2 years? 3 months from inception to production. I'm not making this up. It actually took longer for me to get this through our legal team at ESPN to buy the software than it did to actually build, test, and deploy it.
All right, this presentation was a pretty good example of the extreme scalability of systems. So for the individual participation this week, pick one of the questions that are listed on the discussion forum. Not all these questions will be available, but pick one of the questions and thoroughly answer for individual participation for the week. Again, if you have any questions, let me know regarding this participation for individual video cases. Here are some reasons why we've evolved so much in the last 20 years. If we look at the Moore's law of microprocessing power, perhaps no other law holds as much weight to the evolution of computers as Moore's law. Take a moment to visit the website and describes it more in detail. It's at www.intel.com/technology/silicon/Moore's law/index.html. Microprocessor chips using transistors have helped increase computing power exponentially. However, nanotechnology is the promise of the future. This new technology is being developed because of the limitations of the older technology. Variants of Moore's law include the number of transistors on a chip doubles over 18 months, computing power doubles every 18 months, and the price of computing falls by half every 18 months. Even now, this trend is likely to continue, with transistors reaching the sizes of viruses, the smallest form of life. We look at the law of mass digital storage. As the amount of digital information expands, so too does our need and desire for more storage. In the earlier evolution of computing, storage needs were based on written text. Now we need the extra storage for photos, music, and video. How much storage does the average user really need? Is it the chicken or the egg syndrome? Give me more storage and I'll find something to do with it, or I now have all of these applications, therefore I need more storage. One thing is certain, users will demand more storage and technologists will develop it. According to Metcalfe's law and network economics, if you build a network of 10 users, you will spend the necessary money for the basic equipment. If you already have the equipment in place, you can add one more user at nominal cost. However, the additional user will bring value to the network far beyond what it costs to add him or her. Looking at the declining communication costs in the internet, one of the biggest drivers in the exploding use of computers is directly attributable to the internet. It gets cheaper every day to connect to the internet because of declining communication costs. As more and more users connect to the internet, businesses must find ways to meet the expectations and demands of users, especially in the areas of mobile computing devices. So standards and network effects. Nothing has helped grow the internet more than having technology standards in place, allowing suppliers to create and build products that work seamlessly with each other. Users have to come to rely on the interoperability of products. So the bottom line, we've come so far, so quickly in the evolution of technology. From massive, expensive mainframe computers to inexpensive handheld devices, the evolution and revolution continues. At what point do you believe that the doubling trend of Moore's law might come to an end? Can you speculate and give reasons for your answers? Or do you believe it will continue for as long as we deem in the foreseeable future? What do you think the implications of such drastically reduced costs of computer chips might be in the future? And can you explain the connection to the concepts such as the digital divide and the cloud computing? So packing more transistors into less space has driven down the transistor cost dramatically, as well as the cost of the products in which they're used. And packing more transistors into less space has driven dramatic reductions in the cost and in the cost of products they populate. So nanotubes are tiny tubes about 10,000 times thinner than a human hair. They consist of rolled up sheets of carbon hexagons and have the potential uses as minuscule wires or an ultra small electronic device, and are very powerful conductors of electrical current. They're used to create transistors in the tiny size previously mentioned. Can you describe any other applications for this type of technology? Maybe example would be medical uses. The importance of the exponential growth in hard drive capacity, which is that the world is producing an increasing amount of digital information requiring storage each year as well. Fortunately, the cost of storing that information is decreasing at an even quicker rate. This figure displays the number of kilobytes of data that can be stored with $1. The y-axis is greatly compressed to display the doubling effect, and that if it weren't, the increase from year to year would become increasingly enormous. What if you bought a car that didn't include tires, a steering wheel, a radio, or even a heater? After purchasing this vehicle, you had to shop around for the missing parts. When you entered a store, you were confronted with 8 different steering wheels, 6 different radios, and 9 different heaters. You quickly realize how incompatible the parts are with different brands of vehicles, and wish that the manufacturer simply put all the parts together for you. Once assembled, you drive to the gas station only to realize that your car can't use the brand of gasoline. Pretty frustrating, huh? In part, that is what happened to computers and peripherals over the years. In the early days of personal computers, the printer you had your eye on may not have worked with your brand of computers. You had to buy a scanner built specifically for your computer. You couldn't connect to the internet unless you had the correct modem for the internet service provider. If you wanted to share photos with your friends, each of you had to have 4 different software programs, each of which could process the other's photos. Now expand these examples to the corporate enterprise system. The evolution we are now experiencing is aiming to fix these problems and make computing ubiquitous anytime, anywhere. Let's look at the 7 major components of systems necessary to see us through to this goal. The upcoming slides will go over each component in more detail. Take a look at the example companies that appear under each heading. What companies appear repeatedly? How many items are unfamiliar on this one? Listed here are the major technologies and suppliers for each component that make up an IT infrastructure ecosystem. The microprocessor is the heart of any computing device, no matter how small or large. 2 companies produce most microprocessing chips, Intel and Advanced Micro Devices, or AMD. Although the network is becoming commonplace and the heart of computing, network service providers must have the necessary server backbone in place to meet increasing demand. Blade servers are meeting the needs of service providers more cheaply and more easily than traditional big box servers. IBM offers mainframe computers that can also provide the network processing, although they are more expensive and require Unix software. To give you an idea of the size of the market for computer hardware in 2013, firms worldwide will spend $448 billion on computer hardware. So looking at operating system platforms. Operating systems tell computers what to do, when to do it, and how. Operations such as logging on, file management, and network connectivity are controlled by the operating system. By far the most prolific operating system is Microsoft Windows in various versions. Windows is also one of the operating systems used by mobile computing devices like handheld PDAs and cell phones. Unix and Linux are often associated with large networks that require less application overhead and faster processing. Linux open source software is becoming the operating system of choice for organizations looking to save money. Businesses and governments across the globe are adopting to Linux platform as a way to reduce IT spending and licensing costs. The small mobile computing devices we discussed earlier, cell phones, smartphones, and netbooks, don't have the computing capacity to handle a full-size operating system software program, and many of the functions in Microsoft Windows 8, Linux, and Unix aren't necessary on these smaller computers. Users are opting for lightweight operating systems like Google Chrome and Android instead. Google Chrome operating system is arriving just in time to take advantage of the perfect storm of cloud services, cheap hardware, and a new generation of platform-agnostic users. Unlike other Linux-based operating systems, Chrome has brand recognition that even the biggest neophyte could ever be comfortable with. Chrome is also arriving just in time to take advantage of dirt-cheap hardware and super broke consumers. The future for Chrome-based netbooks is in the $200 and under space. At this price level, Microsoft would have to virtually give away Windows. Within a year or two, netbooks could hit the magical price of $99. For this price, people would happily purchase a computer that is nothing more than a simple and fast web surfing device. While people might expect $300 plus computers to have full-featured operating systems, they may be less critical when notebooks fall into the impulse buy price range, especially when paired with lightning-fast performances. This is according to PC World, titled Google Chrome OS Could Be Pivotal in the Cloud Revolution. This is July 14th of 2009. The Google Chrome operating system makes it easy for users to access cloud computing services through wireless networking. Almost all the software and data are stored on servers and accessed through the web browser. Many smartphones use multi-touch technology that allows users to pinch the screen or swipe their fingers across the screen to issue commands. The new Windows 8 operating software and Apple's iOS extends the technology to full-size desktop and laptop computers. So looking at enterprise software applications. Integrating applications into seamless processes across the organization is the goal of enterprise software applications. Customer relationship management and supply chain management systems are the two most popular applications in this category. We explore them more extensively in later chapters. These applications are becoming popular and more affordable for even small and medium-sized businesses thanks to the proliferation of networks. Microsoft's traditional dominance in operating systems is the most important reason for its success to date. The market for enterprise software application is approximately $250 billion. These applications are considered to be part of IT infrastructure. Traditionally, large firms were the most prominent users of enterprise software, but firms such as Microsoft are trying to move into the untapped market of small and medium-sized businesses that might benefit from less expensive versions of the same software. Today, the proliferation of operating systems for smartphones and tablet computers, mostly iOS and Android, are mounting a challenge to Microsoft's dominance, which depends heavily on the continued existence of personal computers. Businesses and organizations are gathering more and more data on customers, employees, and even the business itself. Managing and storing the data so they are easily accessible and provide meaningful information to the organization is becoming a science in and of itself. Storage area networks, also known as SANs, S-A-N-S, provide a cohesive, economic way of consolidating data from across any and all systems within the business. Online users want instant access to data, and SANs help companies provide it. Remember, the amount of new information in the world is doubling every 3 years, driving the need for more efficient data management and storage. As we continue to march toward convergence of all things digital, networking and telecommunication platforms will merge into one. Rather than having one platform for networking computer devices and a separate platform for telecommunications, we'll see one company providing a combination of telephone services, cell phone, connectivity, computers, and peripheral devices, handheld PDAs, and wireless services are all rolled into one. Many telecommunication companies are now partnering with internet service providers to offer a complete package of digital services. Firms spend about $400 billion a year on telecommunications hardware and $1.7 billion on telecommunications services. The Internet and its technology standards continue to expand the services businesses are able to provide their employees, customers, suppliers, and business partners. Intranets and extranets built on the Internet technologies give businesses an easy and expensive method for providing services that were cost prohibitive a few years ago. If you have any questions related to this presentation, please do not hesitate sending me an email or posting an instructor question in the discussion forum. We will continue with Chapter 5, Part 2.